Just so everybody knows, I will be posting part 2 of this week's homework tonight. It'll be probably about another 30 problems. Yes, I know that is a lot. That is 60 problems this week. But if you tackle them 5 problems a day, or my mistake, 5 problems a day, 10 problems a day, it's about an hour's worth of work, right? Maybe an hour and a half a day. You can get them done in 6 days with a day left over, right? So with that in mind, I just want to let y'all know you are going to have some more homework, and then you're going to have exam 3 for us all next week, and then the final from Wednesday to Friday. We're also going to have one more lecture. It's going to go over chapter 6. It will not be on the final, and it will not be on the exam, but it is material that will help with everything. It'll certainly clear up a lot of what we're going to talk about today. We're also going to have a review lecture on Wednesday. So on Wednesday, bring your problems and questions, and let's square away every last thing we need before the final. I will also be posting the study guides that I gave my students last semester. It will just cover the review sections of all of the chapters that we covered. My suggestion for how to handle those would be just to go through, find problems that when you look at, you know how to solve right away, throw those out instantly. The ones that you pause on and don't know how to solve right away, work those out, do 2 or 3 of them until it becomes muscle memory almost, and go about it that way. Then once you get through a section, go to the next section and keep doing that until you've gotten through all of the problems you don't know how to solve right away. Go back and revisit those problems again. That way you just get that repetition in and you get squared away on any misconceptions you may have. And it becomes one of those things, you see it, you know how to solve it. Just checking really quick. Awesome, everything is good. Sweet. Having said that, let's get into week 13 lecture notes. They cover section 5.4 to 5.6. Starting off with section 5.4. Now, to get into section 5.4, I want us to start making some observations here and start thinking about this idea of area in particular. In all 3 of these graphs, notice that if we were to find the area from x equal to 0 up to x equal to 5, the area changes for each of these, right? Each of these individual lines. So what I mean to say is we've got these graphs that look something like this. We've got 0, 0 here, go up to 5, whatever y is, and find this area. Notice in all 3 of those graphs, like I said, that area changes. And for whatever it's worth, we do know how to find this area, right? It's just the area of a triangle. So you would find the area of the corresponding rectangle and divide it in half, right? So we've got these areas and each one changes. But notice they change in a way that kind of looks predictable by the slope, right? The largest slope would have the largest area. The medium slope would have the medium area, and the smallest slope would have the smallest area. So it's almost as if slope and area are somehow related. And moreover, just looking at these, just really quickly trying to figure out what these triangles look like, right? In that first case, we have y is from 0 to 5 because it's just the equation y is equal to x. In that middle case, we have from 0 to 3 for y. So here, one leg along the x-axis, one of these legs is 5, and the other leg is going to be whatever your maximum y is minus 0, right? So this is the leg that would have 5, 3, and 1 for length, right? And from this, like I said, we can find these areas pretty quick and easily. The area in the first case would just be 1/2 times 25. In the second case, 1/2 times 15, and in the third case, 1/2 times 5. So again, the area under each of these seems to correspond in some way with that slope. And the reason why is because we can rewrite the area formula as the length of one leg times the length of the other leg. This is y minus 0, right? Divided by 1/2. Well, look at what that gives you. That gives you the equation integrated, doesn't it? If the equation for each of these lines is m times x, and the length is the change in x, well, isn't that just the area for, I mean, the integral? Almost. So what this is setting us up for is to recognize that integration, when it's bounded, and I'm going to explain this idea of bounded in a second, but integration, when it's bounded, tells us something about the area of the area underneath the function. But it also somehow relates to slope, which we've seen because the integral, the indefinite integral of a derivative is the original function plus a constant. So what we're getting at here is that somehow area, the derivative, slope, all of these things are intermixed and deeply related with one another. Does that make sense what I mean? Folks at home, does that make sense what I mean?
Yeah.
Cool. So what this bound thing means, what having these a and b means, is that we're going to calculate the integral at particular a and b values, so at particular x values. We call this a here the lower limit of the integral. We call this b the upper limit. And the way we would interpret this is that we're going to apply the integral to our function. Then we're going to take and push b through it and subtract from that the same solution, but instead of b, with a now. But before we get into that, let's just look at what this idea is even saying, based on this thought of it being related to area. Say we've got the function 2x. That's just a line, right? A line with a slope of 2. We know that when we look at x from 0 to 2, this is going to form a little triangle, right? So going back to that drawing, this is going to be the point 0, 0. This here is the point 2, 0. And this is the point 2, 4. And what we are going to find is the area in here. So the area underneath the curve between x equal to 0 up to x equal to 2. This area is going to be equal to the integral from 0 to 2 of the function 2x with respect, integrated with respect to x. Folks at home, can you see the screen on the board?
Not really.
Not really? All right, let's see if I can, that's no better. All right, avoid green today. So this is, like I said, this area is going to be equal to the integral from 0 to 2 of the function 2x integrated with respect to x. But instead of actually calculating this, let's make an observation. We could, let me really quickly plug in. This is the equation y equal to 2x. So before we actually work on this integral, let's make an observation about what that area even looks like. That area, it looks kind of like the triangle with this length equal to 2 and this length equal to 4. We want the area inside of that, right? So we know that that area is going to be 1/2 2 times 4, which is equal to, in our case, just 4, right? So looking at a simple curve, we already know how to calculate that integral. Let's think about how it might relate to the integral itself. If we wanted to calculate it for something more complex, let's say a parabola, and we don't have that easy transformation, right? That easy formula to work with. What that's going to look like to actually calculate one of these integrals. It's going to look like the calculation of the integral, but evaluated at your lower bound and evaluated at your upper bound, and you're going to take the difference between the two. Now, I'm saying a whole lot, and I'm not explaining a whole lot just yet. But that's because I want to first talk about this fundamental theorem of calculus and kind of give you all the context of what we're doing here and how all this relates. So the fundamental theory of calculus tells us that the integral of a function with respect to x between the bounds a and b is equal to the area underneath that function between x equal to a and x equal to b, but it is also equal to the difference of the integral evaluated when x is equal to b and when x is equal to a. Does this make sense, everybody? Folks at home, what I just said, does it make sense?
I think so, yeah.
Okay, so before I move on any further, I'm going to show you exactly what I'm saying. Let's come back to this problem here. Without putting the bounds in, we know that integral of 2x with respect to x is equal to, we can rewrite this as 2 times the integral of x integrated with respect to x. This is equal to 2 times 1/2 x squared plus our constant, right? But that's just equal to x squared. Now, plug in 0 and plug in 2. So what I'm saying now is we're going to add our bounds now. This is equal to, I'm going to use some funny notation and explain it as I go. This is equal to x squared evaluated at 2, and from that you're going to subtract x squared evaluated at 0. Does this make sense?
Yes.
Yes, awesome. So what this bar notation means is that you're going to take this thing, whatever comes before it, and evaluate it at the upper bound and subtract from that the same function evaluated at 0, or your lower bound. In our case, it is 0. Now, a question might occur. Why did I include C here? The reason why I did not include C follows directly from this proof here. Notice that this integral, when we evaluate it just for the function itself, we're not going to include our bounds, we get capital F of x, right? So the derivative of capital F of x plus C, that's just lowercase f of x. That's what we're saying. We're going to evaluate this thing at B and subtract from it the same evaluation, but this time at A. That's what this is saying here. But when we rearrange everything, we get f at B minus f at A plus C minus C. So these two C's are going to cancel, and you're just going to be left with f at B minus f at A. And because of this, your constants drop out every time. And because your constants drop out, it is okay to go ahead and just say, we're going to evaluate x squared from 0 to 2. And that's why I wrote it this way, and why that C disappeared. I should have had it here, though. Is everybody cool with this? Now, some more points about just different notation. Notice they use a square bracket, I use a bar. You can see it also with a rounded bracket, that's a lot less common. You can see it with a closed square bracket. You can see it a bunch of different ways. But all of this says, whatever is preceding, go ahead and group it together, right? So just some points about all of this, some properties of the what's called the definite integral. Pretty much all the same rules. All the same rules. We've got the addition and subtraction rule. We've got the multiple constant rule. Now here things change a little bit, but really all we're doing is breaking up, for example, here, our triangle. We're saying evaluate half of it, then evaluate the second half of it. That is what rule 3 is saying. And it lets you rearrange terms sometimes in a more easy way, a better way to deal with. Notice here, when we evaluate from A to A, all we're going to get is capital F evaluated at A minus capital F evaluated at A, right? So imagine instead of A and B, we have just A and A. Down here, we would have F of A minus F of A. So it would naturally be 0. That's where this rule 4 is coming from. Also notice, if you flip the direction of these. So if you go from evaluating from A to B to evaluating from B to A, you're going in the backwards direction, right? So these get flipped. F at B minus F at A would get flipped in that case. You would have F at A minus F at B. Well, that's just the negative of this. And that is where this fifth property comes from. Is everybody cool with that? So just to better explain and better draw out what this fifth property is. Let me erase this board, or at least part of it. What we are saying in that fifth property is, all right, we've got a function, f of x plus c. We know the derivative of this thing is equal to f of x. So the integral from a to b of f of x with respect to x is equal to f of x evaluated between a and b. But this is equal to, I'm going to use a different color to kind of organize your thought here a little bit. This is equal to f of b minus f of a. But that's equal to negative f of a minus f of b. And we can rewrite this now as f of x evaluated from b to a. And this, my mistake, negative f of x evaluated from b to a. And this is equal to the negative, the integral from b to a of your function f of x integrated with respect to x. So this is where the fifth rule comes from. This tells us directly that when you flip your interval, when you flip your bounds, you have to induce a negative sign. And that's just because we're flipping what's happening here. Yeah. Having said that, again, notice this is the sum and difference rule here. And all of these rules follow directly from this rule right here. So the fundamental theorem of calculus connects all at once area and slope, the integral and the derivative, all in one nice, neat package. Having said that, let's keep chugging along. All right. So in this first example, we want to find the area under the region or under the curve x squared minus 1 between x equal to 1 and x equal to 2. So what is that going to look like? Well, first, let's actually draw this picture and get an idea. So what we've got is a graph that looks something like this. This is x squared minus 1. So we've got a parabola that's shifted down. And the area we're looking for is between 1 and 2. Well, when x is equal to 1, 1 squared is 1, minus 1 is 0. So we're looking from here to about here. So this is 1 comma 0. Up here is going to be 2 comma, in this case, 2 squared is 4, minus 1 is 3. And this point down here is 2, 0. So what we're looking for is going to be the area through here. Now, what does that look like? Let's say we could pull this out and imagine it just as a picture. It would look kind of like a triangle, except the hypotenuse here is curved. Right? Something like that. So we don't have a nice, easy way of calculating this area. You might be able to approximate it by saying, let's imagine we're subtracting part of a circle from it. That might work. Or we could use calculus and directly calculate it. We could say this area is equal to the integral from 1 to 2 of x squared minus 1 integrated with respect to x. Now, based on the rules we just talked about, the sum and difference rule in particular, we can break this up to the integral from 1 to 2 of x squared integrated with respect to x minus the integral from 1 to 2 of 1 integrated with respect to x. This then becomes 1/3 x to the third evaluated from 1 to 2 minus x evaluated from 1 to 2. So putting it all together now, we have 1/3 2 cubed minus 1/3 1 cubed minus 2 minus 1. This is going to come out to be 1/3. This is going to come out to be 8/3. So this whole thing is 7/3, and this is just going to be 1, right? So our answer should be 7/3 minus 1. Does everybody agree? So what is it we just found then? We just found the area underneath that shape, or the area of this shape. So what this fundamental theorem of calculus and these definite integrals let us do is find the area of really weird shapes. Shapes that aren't easy to define their areas otherwise. Yeah. So jumping ahead, looking again at what we've got, it's this area right here. We're integrating from 1 to 2. We're saying, cool, Matt made another mistake. What mistake did I make? I made a typo on my map somewhere. 2/3, that's 248. Oh, no, I didn't. No, I didn't. Once we subtract the 1 here, this is 3/3. So that's going to be 4/3. Minus 3/3 is equal to 4/3. Now notice they didn't use the same rules I just used. They went ahead and integrated all of this together, and I ended up breaking everything up into 2 different integrals. I personally like doing things this way because I think it's easier to worry about each individual piece and then put everything back together, as opposed to having everything bunched up like that, but that's just me. So again, what all of this just did for us is to say that this region, the region between the x-axis and the function x squared minus 1, where x is equal to 1 and x is equal to 2, this whole blue region has an area of 4/3 square units. Does this make sense to everyone? People at home, does that make sense?
Yeah.
Dope. All right. So what about something like this? How are we going to handle that? Well, pretty much the exact same way, right? We're going to break up the integral if we so choose. I personally, in this case, probably wouldn't, just because there's a square here. And why would we? We could use the chain rule if we wanted to. No, let's go ahead and break it up. I think it'll be good practice. Once I get this erased, so we've got the integral from 0 to 1 of 4t plus 1, that quantity squared, integrated with respect to t. When we expand this out, we're going to get the integral from 0 to 1 of 16 t squared plus 8t plus 1, integrated with respect to t. Now we can break this all up and integrate each term individually with respect to t. So we'll have the integral from 0 to 1 of 16 t squared, integrated with respect to t, plus the integral from 0 to 1 of 8t, integrated with respect to t, plus the integral from 0 to 1 of 1, integrated with respect to t. So this thing, well, this thing is going to come out to be 16/3 times t cubed, evaluated from 0 to 1, plus the second term is going to be 4t squared, right? 4t squared, evaluated from 0 to 1, plus this final term is just going to be t, evaluated from 0 to 1. So at 0, everything disappears. So we don't have anything to worry about in that subtraction, right? The only thing that's going to remain are these 1s. So I'm going to go ahead and skip a step and say that since all of these evaluate out to be 0, at 0, we have 16/3 times 1 cubed plus 4 t evaluated at 1 squared plus 1. So this is just going to be 16 over 3 plus 4 times 1 is 4. 4 we can rewrite as 12 over 3. And 1 evaluates out to be just 1. So plus 1 or 3 over 3. So all this is going to come out to be 3 over, this is going to be 18, my mistake, 28 plus 3, so 31 over 3. 31 over 3 square units is the area underneath this curve in between the x-axis. Now, what does that mean exactly? What does this look like? Well, that looks about like this. So it's this weird shape that if we were to pull it out of the graph, would look, if I can draw, would look something like this. Yeah. Everybody cool with that? Now checking out their solution, they do the exact same thing except they use the chain rule, right? That's what they're doing here. That's U substitution being applied here. They're saying, all right, the derivative of our inside is just going to be 4. Well, we can inject that 4 by multiplying by 4 and dividing by 4. That's where we get this 1/4. That's where we get this 4. So that's just multiplying by 1, right? We say, all right, cool, now we have du dx. We have, my mistake, du dt in this case. And we have it multiplied by dt, so we have du. So here we can think of this as just being u squared, integrated, and substitute u back in. And that's how they've gone through this. So having said that, I'm going to go ahead and leave these for y'all to try at home, only because we need to get through some material really quickly. I'm going to jump to this next example. How are we going to handle the absolute value? What's going on here? Let's recall what the absolute value does. The absolute value says if your term, whatever you pass through it, is negative, make it positive, right? Otherwise, just leave it alone. So we've got to ask ourselves what this whole thing looks like, how we can expand it out and work with it. What I mean to say is, since the absolute value of x is equal to x whenever x is greater than or equal to 0, and negative x whenever x is less than 0, what we've got is going to be 2x minus 1 whenever 2x minus 1 is greater than or equal to 0. Trying to get all this written in a nice orderly way. Minus 1 whenever 2x minus 1 is greater than or equal to 0, and then negative 2x minus 1 whenever 2x minus 1 is less than 0. So the first thing we need to do is figure out when these things happen. And since we only have 2 cases, we only need to worry about solving one, because the other one's going to be the remaining the remainder of our x values. Does that make sense what I mean? So whatever x values make this true, after we figure that out, whatever's left has to be what makes this true. Now, if we're dividing by 0, we might need to worry about that a little bit, but we're not yet. We're not there. We're not worrying about that case. So let's solve this. We've got 2x minus 1 is greater than or equal to 0. Add 1 to both sides, and we get 2x is greater than or equal to 1. Divide both sides by 2. We get that x is greater than or equal to 1/2. So what are we going to do here? This just told us that when we integrate from 0 to 2, we have two different functions that we're dealing with. This thing that we're looking at looks about like this. Let me grab the red. This is 1/2. Oh, no, not what I wanted to draw. Half minus 1. So that's going to happen here. At x equal to 0, you like that. Yep, cool, got it. It's gonna look like this, right? Wait. I can't draw this graph today. I don't know why. So let's see if I have it right there. Yes, awesome, I do have it. So what we're doing is graphing, or is finding the area rather, through here. Right? Well, this area is going to behave differently than this area. And this part of the function acts like a different function than this part of the function. So what this is telling us is we're going to have to break our integral up into two different parts. What that's going to look like then is going to be that the integral from 0 to 2 of the absolute value of 2x minus 1 integrated with respect to x is equal to, well, let's break this up into two different parts. The first part is from 0 to 1/2. In that region, our function acts like negative 2x minus 1. So negative 2x minus 1 dx plus the other half of our function, well, it's going to act like 2x minus 1. And that's going to be from 1/2 to 2. And the rule we're taking advantage of, getting back to that slide, it's this rule right here, right? We're saying, yeah, we've got a c between 0 and 2. That c in our case is 1/2. So we can break up the integral from a to b to be the integral from a to c plus the integral from c to b. Because our function changes behaviors. It says from 0 to 1/2, well, from 1/2, negative infinity to 1/2, it acts like this. And from 1/2 to infinity, it acts like this. So because of this, yeah, it's the same thing. It's still the same function. I'm just breaking it up by its behaviors. That's totally okay. Is everybody cool with that idea? Folks at home, are we cool with that idea?
Yep.
Dope. So what this is going to mean for us then is that when we integrate it, we're going to integrate this first part from 0 to 1/2 to get negative x squared plus x, right? Because we're distributing this negative sign all the way through. This is going to be negative 2x. This is going to be positive 1. The integral of negative 2x is going to be negative x squared. And the integral of 1 is going to be x. So that matches. And over here, the integral of 2x is going to be x squared. And the integral of negative 1 is going to be negative x. So that matches. Checking our bounds from 0 to 1/2. All right, cool. Checking our bounds over here from 1/2 to 2. Dope. Everything's checking out. And then we just plug in our numbers, right? We come over here and we say, all right, cool. Evaluate this thing at 1/2 and subtract from it the same function evaluated at 0. That's these first two set of parentheses. Then come over here, evaluate everything at 2. And subtract from it everything evaluated at 1/2. Evaluated at 2, evaluated at 1/2. And from here, it's just arithmetic. So, coming back to this idea of marginal analysis, one way we could calculate differentials or changes rather in R is by integrating the derivative of anything. In this case, we're looking at revenue down here. So to calculate delta R, one way we could go about it is to say, well, what's the derivative of R? That's dr dx. Now let's integrate it from 1 to 2. This is the exact same thing as delta R, isn't it? So this gives us a way of comparing the derivative and the delta value. Does that make sense to everyone? Back home, does that make sense? I'm going to take the quiet stoicism to mean yes. I'm going to jump ahead now. I'm going to jump to example 6 in these slides. We'll say go. All right. We're going to use this idea now. We want to find the change in profit modeled as a function of the number of units sold. So P represents profit, X represents the number of units sold. And what you want is delta P from X equal to 100 to X equal to 101. But you don't know P. All you know is the derivative of P with respect to the number of units being sold. You're given dP dx. You say, damn it, all right, I wanted the actual change in profit. All I've got is a derivative. What am I going to do here? Well, you're going to go ahead and plug this thing through the integral and say, cool, I know that dP dx is equal to negative 0.0005x plus 12.2. So because I know that, I know P is equal to the integral of dP dx with respect to x. So this is negative 0.0005x plus 12.2 and this is p as a function of x. Well, because of that, delta p is going to be equal to p at 101 minus p at 100. Well, this thing is equal to the integral from 100 to 101 of dp dx integrated with respect to x. Because of what we just wrote over here, we know how exactly how to solve all of this now. Does that make sense what I mean? So sitting down now and actually doing this, I'm going to say, cool, this is equal to the integral from 100 to 101 of negative 0.0005 x plus 12.2 integrated with respect to x. Forgot my differential here. Well, I know exactly what this is, right? I know how to integrate that. Because all we're going to do is figure out what that is and then apply the bounds, right? Well, this over here, we know is negative 0.0005 over 2 x plus 12.2 x plus c. But we know that constant's going to disappear in a second, right? So when we come over here to put everything together, I'm just going to delete that constant because we already know it's going to cancel out in the subtraction. So we come over here and we say, all right, that integral is pretty easy to solve. This was negative 0.00025. That was supposed to be a 5. I forgot the square here. Squared plus 12.2 x evaluated from 100 to 101. Well, we know how to do this. This is now just arithmetic, right? You're going to plug in 101 into each of these values. Then you're going to subtract from it the same thing, but with 100 plugged in. That's it. That's all she wrote. So looking, the change in profit comes down to 12.15, $12.15. And all we're doing is using marginal analysis here. We're saying, cool, I know the derivative of my profit with respect to the number of sales we've made. And because I know that, I know when I integrate this thing using a definite integral, that's going to be equal to the change in profit between those bounds. So, just to clarify some terminology really quickly. I keep talking about this idea of the definite integral. The definite integral is what we have written here. It's the integral, but with bounds. If a to b wasn't here, we would call that the indefinite integral. So just as some clarification, this is the definite integral. The indefinite integral would just be missing a to b. So looking from side to side, indefinite integral, notice there's no bounds. Definite integral, notice there's bounds. So here, we're just calculating a function. Here, we may be calculating a function or we may be getting a value out. It depends on how everything's set up. But this, the indefinite integral, typically it's going to give you a function back, not a constant, typically. Cool? Now, having said that, we've got this other idea of the average value of a function. And personally, I don't think this definition is exactly clear. Like, why is this the average value of my function? Why is that? What's happening here? Who thinks they know why this is the average value of a function? Well, what the integral is doing is finding the area, right? So let's say we've got a weird shape like this. This represents x equal to a. This is where x would be equal to b. And the entire length is going to be b minus a. Right? Folks at home, can you read that?
Yeah.
Yeah, awesome. So this area let's think about it for a second. Area we know for a square is just going to be, or for a rectangle, it's going to be width times height, right? Now let's say this was found using a constant function. Y is equal to a constant. Okay. And we were to break this up like this. We get x is equal to a. We get x is equal to b. Before I go any further, what's the average value of this function? Well, it's a constant function in this case, right? So it's just a constant. It's just going to be c. And the area of this thing, well, it's going to be c times b minus a, right? So if we were to integrate c with respect to x from b to a, that's exactly what we're going to get. It's just going to be c times b minus a. Now divide both sides by b minus a. Lo and behold, you get c back. That's because c is the average value of this particular function, right? And in this way, it kind of makes some sense. Nothing's changing in our function, so the average value should be c. This is a pretty easy case to see. Now, what this average value function is essentially doing is saying, hey, if I could turn this thing into a square with the same width, x equal to a and x equal to b. What would the height of my square have to be? Well, that would be the average value of your function up here, right? So what we're doing then is we're saying we're going to integrate this function from a to b and divide by the width so that we can find that height, which is the same thing as the average value of your function. Does that explanation make sense to everybody? Folks at home.
Yes.
Dope. All right. So using this idea, we're gonna find out what the average cost of a CD is, of a CD player is, over a 2-year period. So for my Zoomers in class, a CD player is what we used to use to play music. I kid, I joke. What we're gonna do is we're gonna say, cool, we know the cost of this thing. We're gonna integrate the cost of this thing from A to B with respect to time. We're gonna divide out the difference from A to B. This is what we're gonna do. That's because that's gonna give us the average cost over that period of time. So erasing the board. This is going to be from 24 to 0. 1 over 24 minus 0 times the integral from 0 to 24 of our cost function, which is 0.005 t squared plus 0.01 t plus 13.15. All this is integrated with respect to time. Well, obviously we can rewrite that fraction right away, right? 24 minus 0 is just 24. So let's go ahead and do that. Now, again, I think it's easier to go ahead and break this up into 3 different integrals. But something happens here when we do that. We have to make sure we multiply each term by 1 over 24, right? Because we're multiplying the entire integral by 1 over 24. So we're saying, all right, we've got 1 over 24 times the integral from 0 to 24 of 0.005 t squared, integrated with respect to t, plus the integral from 0 to 24 of 0.01 t, integrated with respect to t, plus the integral from 0 to 24 of 13.15, integrated with respect to t. We're going to close that bracket. Now we're just going to go through and do the calculus. Say what I've got now is 1 over 24 times 0.005 divided by 3 times t cubed, 0.005 divided by 3 times t cubed, but evaluated from 0 to 24, plus 1/2 0.01 t squared, so 0.005 t squared, evaluated from 0 to 24, plus 13.15 t evaluated from 0 to 24. We need to close those brackets, right? And now it's just straight arithmetic. So notice the first thing we do is we evaluate the integral and then we apply the bound, right? So we evaluate the integral, then we take that result, we evaluate it at the upper bound and subtract from it the evaluation of that previous result from the lower bound, or the lower bound from it rather. So what we find then, when we do this calculation, it's going to be that the average cost is $14.23 over a 2-year period of time. And if you look at this function, it's kind of obvious, right? Like if you were to look at that area and compare it to the area through here, it doesn't quite look like it ought to be conserved, but that's largely just because the way that line is drawn. It actually is conserved on both sides. That's what this is saying. Make sense what I mean? And it, because of that, means that wherever those two switch at, that's got to be the middle, right? Now think about why that is. Why is it that the area between this dotted line and our function should be the same as the area between our function and this dotted line over here? That's an interesting question, but it derives from the same idea, the same principle. So when we look at everything, go through the calculation, notice they don't break up the integral again. Part of the reason why they're not doing that is because, like you've seen over here, it gets messy in the notation. That's part of their logic, which I get. That is the downside to writing everything out like this. But it's going to come out to be the same exact thing. Notice also that they use square brackets here, and they say evaluate everything inside in between those square brackets from 0 to 24. So they're just closing the square brackets instead of using a bar to say the term that comes directly before this. Is everybody cool with that idea? People at home, are we cool with that? People at home, you owe me 10 jumping jacks. All right, well, moving on. There are a few other things that are going to be helpful when working with definite integrals. In particular, knowing the difference between an even function and an odd function. In the case that when you pass a negative x value through, it's equal to if you had passed that same value through, but as a positive. If this is true, then it's called an even function. If, however, the sign changes, then it's an odd function. And what this looks like is a reflection in the even case across y. And in the odd case, it looks like a reflection across y is equal to negative x. A reflection and a twist. So you would rotate this quadrant around to that quadrant. Does that make sense? As far as like this idea of rotating from here to here. If it mirrors one side to the other, then it's odd. If when you reflect it across y, they look the same, then it's even. And this is a really convenient fact because what the definite integral is finding is the area between your function and the x-axis. So check it out. The area from here, from 0 to this dotted line, it's going to just be in between here, right? From negative x to that to 0, it's going to be between x and that function again, so it's this bottom part. Well, anytime you're finding the area of a function, and part of it falls below the x-axis, this area becomes negative. It's signed. It's what's called signed area. Signed area is the idea of letting you know where it's oriented against the x-axis. So if your area is positive, the vast majority of your area is above the x-axis. If your area is negative, the vast majority of it is below the x-axis. It kind of makes some sense, right? Like if you're digging a pool, the area you pulled out is negative dirt, right? It's negative volume of dirt that you're pulling out. But once it gets on top of land, you just added volumes of dirt to the top of land. So in the same way that the ground would constitute negative volume or positive volume, depending upon which way you want to look at it, are you taking it out or are you putting it on top of? We have this idea of signed area. That's what this is getting at. Now, because of this idea of signed area, if we were to integrate from negative x to x here, well, check it out. This area in magnitude would be the same as this area in magnitude. So because they're the same values, the integration from negative x to x of an odd function is always going to be 0. Similarly, for an even function, the integration from negative x to x, well, check it out. These areas on either side of the y-axis, they're going to be equal, right? Like this chunk of area over here is equal to this chunk of area over here, right? Does that make sense what I mean? So instead of integrating from negative x to x, why don't you break it off, integrate from 0 to x, and multiply that result by 2? Because evaluating something at 0 is usually really easy. Evaluating something at x may or may not be easy, but 0, usually pretty quick and easy. So an even function, there's a trick we can use, and an odd function, there's a trick we can use. To better explain and show y'all what those tricks are, in the case that your function is even, when you're integrating from negative x to x, or in this case, negative a to a, that is equal to 2 times the integral from 0 to a. Because the half of the area from 0 to a is equal to the half of the area from negative a to 0. Just like we saw here. And in the case that your function is odd, the integral from negative a to a of your function with respect to your variable is going to be 0. So using this, what is b? What do you think b is? Well, first, is b an even or odd function? People at home, what do you think?
Odd?
Yeah, it's an odd function. And we know that by looking at the graph, or we could know that rather by looking at the graph of it. This is x cubed, right? Yeah. Another way we could know that is by saying, all right, let's check out what happens when we define our function to be x cubed and we put negative x through it. All right, we've got f of x is equal to x cubed. Now we want to put f of negative x, or we want to put negative x through it instead. So since f of x is equal to x cubed, f of negative x is negative x cubed. Well, this is equal to negative x times negative x squared. Well, negative x squared is going to be equal to x squared. So we're going to have negative x times x squared. Now we're going to hold on to that negative 1 for a second and multiply x squared by x to get negative 1 times x cubed. This is going to be negative x cubed. Well, that's equal to negative f of x. So your function is on. So what's that integral going to be? What do you think? Our function's odd. And we're integrating from equal bound, right? Negative 2 to 2. It should be 0. This integral here, because the function's odd and we're integrating from let a be equal to 2, we're going to get from negative a to a, then it's 0. Right away, b is 0, without doing any actual integration. In the case of x squared, well, x squared is an even function. We know that because it's a parabola. And we know that negative x squared is equal to x squared. So it's an even function. Cool. So that means instead of integrating at negative 2 to 2, integrate at 0 to 2 and multiply that thing by 2. I'll show you what that looks like. I'm going to show the two side by side. Integrating from negative 2 to 2 of x squared with respect to x is equal to 1/3 x to the third. You evaluate it from negative 2 to 2. This thing is equal to 1/3 2 cubed minus 1/3 negative 2 cubed. Well, this is equal to 1/3 times 8 plus 1/3 times 8 is equal to 2/3 times 8. That took a little while. Now, we know this thing is equal to 2 times the integral from 0 to 2 of x squared dx. Well, again, we're going to have pretty much the same thing starting off. 1/3 x to the third, evaluated from now 0 to 2. Well, there's no point in evaluating this at 0 because we already know this thing is going to be 0. So we're going to get 2 times 1/3 2 cubed minus, like I said, 0. Now that's 2/3 times 8. A lot less work. So knowing these tricks are definitely going to help. They make your work less. They make your work less. Is that good English? Is that proper English? Can I talk goodly? Having said that, there's this idea of an annuity. And an annuity is the sum of all of your payments, right? Like it's the total amount of interest earned, if that makes sense what I mean to say. So naturally, we're going to get interest earned times, how do I want to say this properly? I'm trying to make sure I say this in the best way possible, other than repeating the definition. I guess the definition says it just as well as I could. But the way we calculate an annuity is according to the following integral, right? So you're gonna say, all right, cool. I'm gonna evaluate E raised to my rate times whatever the total amount of time is, T. I'm gonna multiply that by whatever my function of dollars per year is, times e to the negative RT, integrate that from 0 to t with respect to t. For the sake of time, I'm going to skip this example, other than just to show we're evaluating it the exact same way we would any other integral. I've got to get through all of this material today. Having said that, I'm going to give y'all a 10-minute break here. Come back at 7:35.